Thank you so much. Oh, okay. Good morning, everyone. Thank you for the opportunity to speak in the Zoom International Problem Seminar. So my talk today will be on inverse problems for certain nonlinear PDEs. So particularly, I will talk about this higher order linearization approach. Here will be based on the joint work with Dr. Janet Esselbeckhoff and Professor Rui Lai for nonlinear Maxwell's equations and nonlinear magnetic Schrodinger equations. Okay. So let me start with the Cadron's problems that you are familiar with. This is for electrical impedance tomography, as you know, to recover the conductivity function inside the bounded domain from the boundary measurement of the voltage to current map. In this case, it will be the Dirichlet to Neumann map for the conductivity equation here. Okay, so we care about the uniqueness question, which is to ask if gamma, the conductivity, is uniquely determined by the DM map. Okay. Natural generalization of this to electromagnetism would be considered recovering the linear electromagnetic properties of the medium modeled by mu permeability and the permittivity epsilon here in a bounded domain from the boundary measurements of electric and magnetic fields. This is for a fixed frequency, so we consider time-independent harmonic Maxwell's equations. So the boundary measurements in this case as an analog of the DM map would be the admittance map for the tangential electric field to tangential magnetic field. Again, we ask, can we uniquely determine epsilon mu from this admittance map? Okay, so these are all inverse problem for linear equations, as we know. I want to go over quickly this strategy of the proof for uniqueness based on this work by Sylvester and Woman in 87 for the higher dimension, the higher than three-dimensional Cadron problem. Because even for the nonlinear equation inverse problems, we're basically following the same steps by establishing this integral identity and find proper solutions to plug in. Okay, so we know the first step is just take the Cadron problem, for example. So first step is to reduce the inverse problem for the conductive equation to that for the Schrodinger equation by doing a Liouville transform, which is multiplying the original solution by the square root of the conductivity. So we end up with a Schrodinger equation. And assuming the conductivity is determined on the boundary, then we can also get the DM map for the Schrodinger equation. So the whole inverse problem is translated to that for the Schrodinger equation. And for the uniqueness question, we ask if we can show Q1 equals Q2 if the two DM maps are identical. So from this, we can derive this integral identity, which essentially is the integral of the difference of the potentials multiplying the product of the two linear solutions. Okay, and then the question is finding enough solutions so this product is dense and to show Q1 minus Q2 is 0. As we know, the solutions constructed in this paper is so-called complex geometrical optic solutions. The idea is to look at this exponential harmonic. Zeta is the complex vector, satisfying the dot product being 0. And ignoring the remainder at the moment, then for choices of zeta 1, zeta 2, we can find enough Fourier frequency c to get the Fourier transform of the difference. The only thing is how to show this remainder is ignorable, in which sense? In this case will be with respect to the large magnitude of the complex vector. Okay, so these are the conditions satisfied by the complex vector for the CGO solution. Okay. So now let me talk about the nonlinear equation case For example, the Calderon problem, we can assume the conductivity depending at the same time the solution or the gradient of the solution. So again, we take the nonlinear DM map, the boundary, and ask if we can recover the full nonlinear conductivity from the DM map. So here is sort of an early demonstration of the application of the linearization approach to this problem in the case where the conductivity depending on only the solution. Okay, so this is a case that we can recover fully the nonlinearity using the particular fact that any constant is a solution for the equation. So we do this linearization of the DM map by doing the perturbation of the constant solution and linearize with respect to t. You end up with the DM map for the conductivity frozen at the constant function solution. And using the previous result, and for every constant, we can recover the conductivity frozen at that value. Then that means we can really recover the full nonlinear function sigma. So this is the case. One linearization could already prove the uniqueness of the conductivity for the nonlinear equation. Here just list some literature results for the nonlinear equations, the inverse form for nonlinear equations. Some using the linearization approach. Okay. So due to the limit of time, so I just quickly go to the next slide. Okay. To start to model the nonlinear electromagnetism by considering the nonlinear Maxwell's equations. So this is a slide to motivate the whole idea of imaging nonlinear property of the medium, in particular for certain materials or medium, imaging using, for example, second harmonic generation property of the material has its benefit, for example, a better depth penetration and the safer, meaning stain-free molecule contrast. Okay, so here is a list of certain microscopy method using the second harmonic generation effect of the material. I'm not suggesting that the inverse problem I'm talking about here will be modeling any of this technology, but just to say that considering inverse problem for nonlinear Maxwell's equations is important. Okay. All right, so I spent next few slides to explain the model here. So we start with the full Maxwell's equation, time dependent. And here will be the constituted relation. Okay, so you have the linear part, which is still the epsilon mu will be the linear parameters. And we have the nonlinear polarization P and L and the nonlinear magnetization M and L. So in the nonlinear medium, this is a formal format of the polarization. It has a linear part, but for simplicity, I just threw this together with the permittivity, the linear part of the material. And just consider nonlinear polarization, writing formally in this expansion in terms of the powers of electric fields. And the chi here will be the J's order nonlinear susceptibility in front of each term. And in the most general case, these will be J plus 1 tensor, okay, for the J's order susceptibility. So in our case here, we'll only consider two most commonly seen nonlinear effects. One is sort of a second order polarization appearing most common in this non-central symmetric medium, such as the collagen fibers I just showed you. Particular second harmonic generation is corresponding to two photons of the same frequency merge together to get one photon of the double frequency. Okay. Another common nonlinear material would be the sort of third order polarization known as the Kerr type. This is a general case when you have an incident wave with three frequencies, and this will be all possible frequencies generated in this third order polarization. Okay. And for the higher order polarization, you could have sum and difference frequency generation following the same idea. Okay. So I talk about the Kerr type nonlinear medium. As I mentioned, this is one type of commonly seen material, in which case no new frequency photons will be generated. Only the frequency omega will be remain. So it will be the simplest nonlinear medium by only consider one set of Maxwell's equation for a single frequency omega. Another way to understand this medium of Kerr type is to just think of the susceptibility for both electric and magnetic, depending on sort of accumulation of the intensity of electric field or accumulation of the intensity of magnetic field for the magnetization. Okay. Or in terms of the third order polarization, you could consider it's really combining three photons of the same frequency with one complex conjugate to give you still the omega frequency field. Okay. And for the magnetization, this is not often seen in the natural material, but in certain metal materials, you could have this kind of a macroscopic behavior. So this will be the time harmonic Maxwell's equation for the Kerr type nonlinear medium, where you have the cubic nonlinear terms here. And we define the admittance map, still tangential electric field, tangential magnetic field, and asking if we can determine all four parameters from the admittance map. So this is for Kerr type. And it's a little bit more complicated for second harmonic generation, where you have the incident beam for one frequency, and as a result, you generate a new field with double frequency. So your equation will involve like two sets of Maxwell's equation for omega and the two omega. And the coupling of the two equations will happen here. Two fields of the same frequency give you the double frequency. And here, just saying that the double frequency could feed back to generate the frequency omega field as well. Okay, so you have these two terms in the nonlinearity for the second harmonic generation. So in this system, I ignore the nonlinear magnetization, not only because it's not often seen in the natural materials, but just for simplicity of the calculation. As I mentioned, the second order susceptibility would be a three tensor, but here we just assume the isotropic case, which will be just a vector valued function. So we'll recover this vector valued function from the admittance map. Yeah, here we can also introduce a second harmonic generation effect for magnetic fields. And I explain a little bit why we can assume mu and epsilon also depend on the frequency, most because we have more data here, because the admittance map is defined for fields for both frequencies, with electric field, omega and 2 omega. Okay, so using this admittance map, we want to recover epsilon mu and this vector valued second order susceptibility. The next two slides are dense, but just really saying the well-posedness for these nonlinear equations. We all assume that the boundary input, the tangential field being small enough, so we can use the standard Soberly embedding and contraction mapping argument to prove the well-posedness. The other thing is we use LP-based Soberly space for the Maxwell's equations. And same with second harmonic generation here. So the main result here, first for the curve type is if we have identical admittance map for two sets of parameters, then we have identical parameters. And then the second for the second harmonic generation. Okay. All right. So I mentioned brief idea of the proof, which again following very similar to the proof for a Cadron problem. But adopting this higher order linearization approach by consider asymptotic expansion of admittance map. So you perturb the zero solution a little bit by SF or S small. Then this asymptotic expansion for the curve type will be contain the first term and the third order term here. And the first term here, you have the admittance map for the linear equations with linear parameters epsilon mu. So this one we can use to determine epsilon mu. Okay, and the focus is the next term to determine the A and B. And this would be the map from the linear field. E1, H1 would be the solution for a linear equation with the boundary tangential field to be F. Map to the E3, H3 would be satisfying the linear equation, but with a source to be the cubic powers of the E1 and H1 for linear equations. Okay. Using this second term, we can derive an integral identity from the identical admittance map. So this will be the integral identity similar to the one for the Cadron problem for Schrodinger equation. You have the difference of the parameters multiplying by the product of the solutions, and E1 and E tilde, H1, H tilde, these are all solutions for the linear equations. Okay, where we already know mu epsilon are uniquely determined. Okay, so now then we have the integral identity. The next step is just plugging proper solutions. So before that, let me mention the same steps for second harmonic generation, where you have the asymptotic expansions for both frequencies. And the first, again, you can use this to recover epsilon mu. So this is where I mentioned earlier, you can assume epsilon mu depending on omega and the frequency, because really this will be decoupled to admittance map for the two Maxwell's equation for each frequency. So to determine the chi2, the susceptibility, we use the second term here, okay, to derive this integral identity, which is the difference of chi2 for the two sets of parameters, multiplying the product of the three linear solutions. So the omega to omega indicate the frequency dependence, and all these solutions are linear solutions. So here they only have the electric energy. We don't have the magnetic energy because I didn't include the magnetization. So again, we want to plug in proper solutions. So it turned out for these two cases, the curve type and second harmonic generation, at least for our work, we tried several CGO solutions for Maxwell's equations, and some work, some doesn't. So I'm explaining a little bit the reason why some actually works and some doesn't. Okay, but before that, I want to mention quickly the construction of CGO solution for the linear Maxwell's equations, and following the method in Ola and Tomasello. Okay, which is very similar to the Schrodinger equation for the Cadron problem. This kind of Liouville type of transformation. Okay, so you take the Maxwell's equation and adding the divergence-free equations, and then define this divergence to be the scalar potentials. Then the whole system becomes elliptic in terms of the scalar potentials and the E and H. Then after a Liouville type rescaling, then you will get the elliptic first order Dirac operator. That means it's a factorization of the this Helmholtz-Schrodinger equation here. So using this fact, you can first construct the CGO solution for this Schrodinger equation. You construct the CGO solution Y, and go back to the solution for the Dirac system. You just, applying this operator to the CGO Y. And the last step will be, when you have the solution for this system, going back, you have to make sure that phi and psi, the scalar potential, to be 0 to give you the solution for the Maxwell's equation. So that's a little bit extra step you need to check to get the solution for Maxwell's equation. Okay, but the whole idea here is to reduce the Maxwell's equation to the Schrodinger equation. And here is just to summarize the CGO solution for the Schrodinger equation with different phases, because we'll be choosing proper solutions to plug into our integral identity using one of these. Okay, so we have the phase part, the weight, and the amplitude and the remainder. So the remainder will be small comparing to the amplitude as tau, this parameter going to infinity. Okay. The phi here, as we know, is a limiting column weight, and there are just a few of them. So you have the linear weight, the CGO solution we've seen for the Schrodinger equation, and also the nonlinear, this is a limiting column weight phi x taking this format. And also this one is in cylindrical coordinate. This is the limiting column weight, and psi is taking to be just minus r. Okay, so this is a CGO solution for Schrodinger equation. And again, I just want to quickly go over this slide, just saying that go back to the CGO solution for Maxwell's equations. We apply this operator to this YCGO and write it in the CGO format, and just check that the component for the scalar potentials phi and psi to be 0, so that really we get E and H to be the solution for Maxwell's equations. So it's a little bit technical here, so I'll just skip this. You know, that's just going back to the Maxwell's equations. Okay, so now we have the CGO solutions with different phases using the Euler-Sommersello construction. Oops, sorry, okay. And now we are ready to try CGO solutions in our integral identities. First, we tried the linear phase CGO solutions and plug into this curve-type integral identity where we have the product of 4 solutions. Okay. This would be the CGO solution we use first. We tried first. S0, T0 will be the two, we have the freedom to choose these two constants. If we choose 1, 0, then we just promote the electric part and ignore the magnetic part. Goes to the lower order terms. And the other way around, the 0, 1 will give us sort of reconstruction of B instead of A. Okay, so, and then just notice that the Euler-Sommersello construction amplitude part will be essentially theta 1, the same as the linear weight. Okay, so we tried these solutions. However, we don't have enough choices of these complex phases such that this product give us, as before, the Fourier exponential for enough directions to see. First, we thought it's just we didn't do enough polarization, meaning that here we have a product of 3 same solutions. But if we kind of split this solution into 3 things, and then we can have something like this, meaning the product of 4 solutions, each of these 3 to be a linear solution. So we have more freedom to control this. Of course, you can think of this to do the polarization at the very beginning for the asymptotic expansion for the admittance map, going epsilon 1, epsilon 2, and epsilon 3. Okay, it's the same idea. However, we tried and somehow still we couldn't match enough CGO solutions to give you enough free the free transform for enough directions. Okay. I think the reason is the following. So I can explain a little bit using the cut-around problem for the linear equation. So on the right here is the steps to show the uniqueness for cut-around problem, where we reduce to the Schrodinger equation using the Schrodinger DM map and construct this integral identity for the Schrodinger equation and using the CDO solution there. And everything works here. Of course, you can do the same for the cut-around problem using the conductivity equation directly. You can still derive an integral identity, which is the difference of the conductivity multiplying the product of the gradient of the solution. And then you use the CGO solution. Keep in mind that's just a Liouville transform of the transform back of the Vj here. So this will be the product of two gradient, okay? And here would be the gradient. So the gradient will give you the amplitude to be zeta1 dot zeta2 here as the first term. And the problem here happens that when zeta j satisfying all these conditions, at the same time, you want zeta1 dot zeta2 still dominate the other terms. Somehow we couldn't preserve this property, preserve the domination of this zeta1 dot zeta2. Okay, so that's the kind of the issue also we run into when we try to plug in these linear phase CGO solutions. This is very similar to the one we just seen because the amplitude is just the same as the weight here. Okay. So this is just to show you you have a similar idea for the inverse problem for linear Maxwell's equations. And this is on the right would be the strategy used in the Ola and Somersello's proof using directly Schrodinger equation, second order Schrodinger equation to derive the integral identity. But to the left, if we directly derive the integral identity from the Maxwell's equation, so you have E1 and E2 here is essentially is the gradient of U1 and U2 in this case. So you will still have the zeta1 dot zeta2 there, and they cannot dominate. So then we just go to the other choices, and we found that using this cylindrical limiting column ways, CGO solutions would work. So these will be the choices of the 4 solutions we plug into the integral identity. And this is the LP decaying for the remainder part. And after that, we have obtained sort of attenuated geodesic transform of the Fourier transform of the difference of the parameters in X1. And using the uniqueness for this 2-dimensional attenuated geodesic transform, we can derive A1 equals A2. Okay, so that's how we solve this Kerr-type uniqueness question. And for the second harmonic generation, things are a little bit different. Again, we tried this CGO solution with linear phase in Euler-Somersello's construction, and kind of different issue arise here. But I just want to mention how we solved it. We go back to the Euler-Perrenta-Somersello's proof for the uniqueness for the linear equation for Maxwell's equations, linear Maxwell's equations, which is before Euler-Somersello's approach. So here would be the CGO solutions considered there. The only thing different from Euler-Somersello's CGOs here is the amplitude actually is no longer just a zeta1, the linear phase. It actually satisfies the dot product of the linear complex vector dot product of the amplitude will be 0. Okay, so it's different from before. And we can find these 3 fields multiplied together. This is the first term here to give you this enough Fourier exponential for enough Cassi, and with the amplitude A tilde omega. And if we choose A tilde 2 omega to be 0, And this second term here becomes a lower order term. Okay. So we will have the Fourier transform of the susceptibility dot product with the amplitude of A tilde omega. Okay. So as I mentioned, for this CGO solution, you only need the amplitude and the phase here to be, sorry, the dot product, those two will be 0, as I said here. So we have some freedom to choose this amplitude here. One is to choose such that this dot product equal to 0 for all the perpendicular direction to the Fourier direction C. Okay. And which implies the curl of the vector will be 0. And also dot product with C itself will be 0, which gives you the divergence being 0. So all these two facts together give you the chi1 equals chi2. Okay, so we can uniquely determine the vector value, the second order susceptibility in this case. Okay. So that's the end of the proof for the second harmonic generation, where we use the Euler-Pivarental-Sommersalos construction of the CGO solution. Okay, so that's the story for the nonlinear Maxwell's equations. Then this third part have about 18 minutes. I talk about the result for the nonlinear magnetic Schrodinger equation with partial data. So using this higher order linearization approach. So this is a nonlinear magnetic Schrodinger equation we're considering here. D here is the Fourier gradient. And A here is the magnetic potential, it's a vector value. Holomorphic in the second variable, so we can have the write it as the Taylor expansion. Same with the electric potential, scalar function holomorphic in Z as well. And we have this condition at 0, A and Q to be 0, just to guarantee 0 is a solution for the equation, so we can do the linearization. And this second condition here is to make sure that the linearized equation for this nonlinear equation is just Laplace equation. Okay, so we can use the solution, the harmonic functions in our integral identity. Okay, and this inverse problem is to recover A and Q, or more specifically the terms in the Taylor expansion coefficient when Z is 0 from the partial boundary Dirichlet to Norman map. Here, the Dirichlet data is supported on gamma 1 and the Norman data is supported on gamma 2. And the thing is, gamma 1 and gamma 2 here are arbitrary open subsets of the omega, so which is kind of different from the partial data result for linear equations. As many of you know, there usually you have some geometrical restriction to the accessible boundary. Okay. So let me just take K equals 2, for example, recover the second order term in this expansion for A and Q. Now we use the second order linearization in the asymptotic expansion of the DM map. Okay. As a result, we can quickly derive this integral identity using 3 linear solutions, V1, V2, and V3, where V3 actually is in this coupling of magnetic potential and electric potential. So A tilde will be the difference of the first derivative in Z of the 2 magnetic potentials, and Q tilde will be the difference of the second derivative at 0. Okay, so we want to show that A tilde and Q tilde are 0 from this integral identity. Okay, and this is only true when for the partial data when V1 and V2 are supported on gamma 1, where V3 is supported on gamma 2. Okay, so these will be the conditions that make things a little bit more complicated. Otherwise, since V1, V2, V3 are just the solution for a linear equation, in which case it's just harmonic functions. So we have many choices to make this work. So here are some results as a comparison for some linear equations. First, this is for only the electric potential without the magnetic potential, and reduced to the power type nonlinearity. And here in paper by Katja and Gunther, they considered the nonlinearity in the gradient of the solution. It's similar to a magnetic potential case. And on the right will be corresponding integral identities for these two cases. This will be the solution of m+1 linear solution, product of m+1 linear solutions. In this case, will be just harmonic functions. And here will be the product of the gradient of two harmonic functions and the third one. Okay. So let me go back a little bit to the partial data inverse problem for linear equations. In this case, for the Schrodinger equation, linear Schrodinger equation. There are many results for this problem using the Kalman estimate to construct CGO solutions that vanish on part of the boundary. Okay, and there are some geometrical restrictions on gamma 1 and gamma 2. Another comparison to get the same kind of integral identity, but this is U1, U2 will be the solution for the Schrodinger equation. Hence, the difficulty is to construct these CGO solutions. And here, if we do the linearization of the inverse problem around the potential Q equal to 0, so you will have integral identity like this with V1, V2 being the harmonic function. So this is similar to what Cadron was looking at. But for the partial data problem, you need them to be vanishing on the corresponding part of the boundary. So this is the second one here is considered in this paper, where they basically show the density of the product of harmonic functions which vanish on part of the boundary to be dense in L1. Okay, so the solution they are using is having this again exponential harmonic function and plus a little bit W. So H here will be a small parameter, and the zeta here is a complex vector. It's the dot product being 0. Exponential harmonic, and W here is just take care of the vanishing part of the boundary, so cancels the harmonic on gamma so that the solution vanished there. And they use these solutions in the integral identity, and they can derive this kind of exponential decay with respect to H. For those directions, for those zeta 1, zeta 2, the sum actually is near this axis. Okay, so this coordinate is set up on the boundary near the part at the point where at the point on gamma. Okay. And then they use this kind of watermelon proof to show the extrapolation of the exponential decaying to other directions. So you have enough frequency to really show this actually vanishes. Okay. So for our result and also for the result I mentioned earlier, we directly apply this result, the density conclusion. Okay. So here is just demonstration for the earlier result when you have the power type nonlinearity. This is integral identity, and you can use the density of product of two solutions to arrive this to be 0, and choosing other harmonic functions to be non-vanishing in the domain one way or the other. So you can show Q1 minus Q2 is 0. And this is for the other case when you have the nonlinearity in the gradient. So in the paper by Katja and Gunther, they modified the proof to show that the product of the these harmonic exponentials actually are also dense in the in the space, in the function space. So you can show Q1 minus Q2 times another harmonic function to be 0. So for us, we do the same. This is our integral identity, and the V1, V2, we use the density of this product. So quickly we get the red part to be 0. Okay. Keep in mind, we want to show A tilde and Q tilde, they are 0. Okay. But directly from this equation, it's not so trivial. So naturally, we just use V3 to be this harmonic exponential again. Keep in mind, V3 also is vanishing on outside gamma 2. Okay. So we use this harmonic exponential here. And it's not hard to see because it's after taking the gradient, you would have this term first dominate the other terms. So asymptotic in terms of H will give you A tilde dot zeta equal to 0. Okay, so again, let me go back one more time. Here, the zeta comes from the derivative of the gradient of V3 from this exponential. W3 again is controlled by this exponential decay. And that's only locally near this boundary point of gamma 2. Okay. So this allows us to show A tilde equal to 0 in a neighborhood of gamma 2. Okay, not globally, because passing a little bit far away from this boundary point, the exponential decay of W3 is not guaranteed. So we cannot directly derive the global uniqueness from this. However, we just use adopt the bootstrap local to global step that was used in the density proof earlier to show using a wrong approximation approach to show A tilde equal to 0 in the whole domain. Okay. And lastly, this gives us the Q tilde equal to 0. So this will be the final touch in our result to show the uniqueness for the magnetic Schrodinger, nonlinear magnetic Schrodinger equation. This is for the, of course, only for k equals 2. Okay, in the Taylor expansion, you can do this for the higher order terms. Okay, okay, so that would be the result for this paper by Wu and myself. I guess to summarize, then we basically take this higher order linearization approach and plug in different types of solutions. And for CDO solution for Maxwell's equations, depending on which nonlinearity we're using, and this exponential harmonics for this scalar magnetic Schrodinger equation. Okay, thank you for your attention. That will be all.
Thank you very much, Ting, for the very nice talk. Thank you very much. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself.
Yeah. Should I go back a little bit?
Yeah. Ting, by the way, you mentioned on one slide, I mean, about some results about nonlinear Maxwell equations on admissible manifolds. Are there any results? I mean, on one slide, it was written something about this admissible.
Right. Yeah, I guess, yeah, here.
Generalization to admissible.
Right. We didn't go over the argument for general admissible transversely anisotropic manifolds yet, but just because we use this CDO solutions that was constructed originally on this admissible manifold, so we think this should be able to extend the method to those cases as well. Yeah.
I see. Thank you very much. Thank you. Are there any other questions or comments, please? Okay, if not, thank you very much, Ting, for the very nice talk. Thank you very much everyone for coming. Thank you. Thank you.
Thank you. Okay.